Let us discuss few examples as far as simple harmonic motion that is concerned. We have in fact different cases. The very first case we are going to deal with is simple pendulum. So let us take the oscillating pendulum. The oscillations of a simple pendulum are considered to be simple harmonic. Let me remind you all the formulae related to this first. When we consider a simple pendulum of length L, which is suspended from a point O and of course having mass m, you can all understand well length is measured from the point of suspension to the center of mass of the bob. Now this is the simple pendulum. It is now brought aside to a point say B from this point A, and it is now left so that it oscillates simple harmonically to and fro with respect to the mean position of rest, that is A. Let us once again consider here the angle what it is making, the string is making with the vertical, that is taken as theta, and its mass remains as it is, that is m only. Now in this regard, we all can understand well weight is acting vertically down and the tension in the string that acts towards the point of suspension. These are the direct forces what we can understand as far as the situation that is concerned. When this angle is theta, I now can write the components of this weight by considering this angle again as theta. We now get mg cos theta as the component of weight here, and along this direction the component now becomes mg sin theta. So the moment we are taking up all the different forces acting on that, one can understand that the tension and mg cos theta, since they are acting on the same line in opposite directions. Not only that, due to the application of these two forces, this block or this particular bob neither is going in this direction nor is going along the direction of mg cos theta. So what is the conclusion over here? You can say these two are compensating each other, they are equal and opposite. So first and foremost concept we can understand is that the tension in the string is equivalent to the component of weight, which is mg cos theta. Come to the next one please. What is the resultant force that is acting on the bob, or what is the force by means of which the bob is trying to come back to its normal position of rest? That of course is mg sin theta. This is what actually one has to remember. Suppose if I consider a special case here, if theta is very small according to physics, not necessarily be 0. It will not be 0, of course it cannot be, because when it is oscillating definitely there will be some angle. That angle should not be more than 5 degrees, generally what we used to consider is that. So when theta is very small, sin theta now can be written as theta. In fact, we have a small concept in mathematics under limits. Limit theta tends to 0, sin theta by theta is 1. So automatically sin theta can be written as theta by cross multiplication of that. So this is the conclusion. Therefore, what would be the resultant force acting on the bob? That now can be taken as mg into theta. When this is the resultant force, what would be the acceleration of the bob now? That is the next concept. Acceleration, when we talk about, it can be written as g theta, because force by mass is acceleration. We all can understand from this equation that acceleration is equal to g theta. That is one area. Come to the second point. If at all you are making the bob move from A to B, are you not making it move along a small arc there? If you consider OAB as a sector, a part of a circle, then we can write the next concept over here. From the sector, what is that sector over here? OAB. You can understand AB is equal to radius times the angle of the sector. And what is this AB also we can understand straight away here. That is the displacement of the bob. Therefore, we can rewrite the same this way, that displacement of the bob is equal to r theta. This is the next equation one has to remember. So, individually when I remind you all the formulae here, these are the major equations one should have in memory. So, this is acceleration part of it, that is the displacement part of it. But every one of us we know directly that time period of any body which is in simple harmonic motion, t is equal to 2 pi under root displacement by acceleration. This is the basic equation what we have taken up in this chapter. So, 2 pi root displacement by acceleration. What is the displacement here? R theta. That r theta we can even write that one as L theta here. Because what is the radius of this particular circle? It is nothing other than length of the pendulum. Therefore, we can write this one over here to complete the equation. T is equal to 2 pi root L by G. This is one formula we need to remember. And what would be the next equation? What would be frequency? Frequency of oscillating pendulum is 1 over time period, which can be taken 1 by 2 pi under root G by L. This is another equation we need to remember. Come to the last one, that is what would be its angular frequency. Angular frequency is nothing other than omega, which can be taken as 2 pi n, which now can be written as under root G by L. So, these are the major equations one need to remember as far as a simple pendulum that is concerned. But these equations directly may not be asked in the examinations, particularly competitive examinations. They used to take their applications. So, what are those other applications related to these equations? Let us discuss in a detailed way. Since we know the value of time period of a pendulum as 2 pi under root L by G, we can write that acceleration due to gravity G is equal to 4 pi square L by T square. So, every one of us can understand directly at a particular place, acceleration due to gravity remains constant. Therefore, what is the next concept we need to know? L by T square remains constant at a place. L by T square is remaining constant means you can directly understand L is proportional to T square. So, when I just plot a graph between L and T square, I be getting a straight line passing through the origin. Not only that, when we just plot a graph between L and T, we be getting a curve like this. That is one zone which we have to concentrate on. Coming to the next one, there is one particular kind of a pendulum which is called seconds pendulum. What is a seconds pendulum? The time period of a pendulum, it is exactly 2 seconds. That is what we call it as seconds pendulum. And what are its individual features? Seconds pendulum's time period is 2 seconds, and of course its length on the earth is nearly 1 meter. And we all can understand well what would be its length on the moon. You can take it's around 1/6 of a meter. Because we all know well the acceleration due to gravity on the surface of the moon is 1/6 the value on the surface of the earth. Therefore, we can write it is nearly 1/6 of a meter over here, that is 1. Now, one more question, how many times does a seconds pendulum oscillate in a day? In one day, we have 86,400 seconds. Out of all, for every 2 seconds, that seconds pendulum completes one oscillation. Therefore, how many oscillations it will make now? 43,200 oscillations per day it's going to make. 86,400 divided by 2. So, 43,200 oscillations it will make in a day. That is one more point. Now, here a technical concept like they may ask you. For a seconds pendulum, for example, we have plotted L versus T square graph and L versus T graph both on the same graph paper. LT square graph will be a straight line and LT graph is a curve. Both are going to cross each other at a particular point. Then what are the questions they may ask you? What would be the corresponding length at that point of intersection? And what would be the corresponding time at the point of intersection? Corresponding to this point of intersection P, the time period T will be 1 second. And this length is going to be exactly 25 centimeter. Or you can even call it as 1/4 a meter. So, remember, when both the graphs are plotted on the same graph paper, that too for a seconds pendulum, then there will be a point of intersection like this. At this particular point or corresponding to this point, what would be the length of the pendulum? That is 25 centimeter. What would be the time period corresponding to that point? That is going to be 1 second. So, this is one more point we have to remember. Come to the next one, please. When we consider n is equal to 1 by 2 pi under root g by L. That is the basic equation what we have taken for a simple pendulum or oscillating simple pendulum for its frequency. Then you can understand here the first condition, n is directly proportional to root under g if I say L is kept constant. In the same manner, when I take n is inversely proportional to root under L, if I consider g is constant. G is constant means at a particular place, when I just relate n with L, automatically one can understand n is inversely proportional to root L. Coming to the third one and the last in this order, G and L are directly proportional to each other. This is the case when I consider n remains constant. In fact, these three equations, we generally call them as laws of a pendulum. So, what are the different laws of pendulum means? How this frequency of oscillating pendulum that depends on different aspects according to this equation. That is what we just want here. So, these three equations one has to remember as far as laws of pendulum they are concerned. Let us take few cases as far as a simple pendulum that is concerned. Few cases in the sense, there is one option like this, they may ask you a lift problem. What is this concept of lift problem here? Let me explain you. There is a pendulum which is oscillating simple harmonically in a lift. The length of the pendulum will be given to us and mass of the pendulum will be given as m. and they used to give us few conditions as far as the lift that is concerned. First one, lift is at rest and the pendulum is oscillating simple harmonically. Every one of you can understand directly, when the lift is at rest, the time period of the pendulum, or even for that matter its frequency of oscillation, both will never vary. Therefore, we can write directly T is equal to 2 pi under root L by G and N is equal to 1 by 2 pi under root G by L. So, as long as the lift is at rest and the pendulum is oscillating suspended from its roof simple harmonically, there will never be any change either in the frequency part of it or in its time period. So, everything will be normal. Now, let us consider the second case here. If the lift accelerates uniformly upwards at A, the acceleration with which it is going up is uniform acceleration and its value is given as A, then what happens first of all? The relative acceleration now becomes G plus A. Every one of us can understand straight away, when A is upward and G is acting vertically down, the relative value will now be the sum of these two values, which is G plus A. Therefore, the time period becomes 2 pi under root L by G plus A. What you can infer from this? Time period decreases. Because the denominator is increasing here, automatically one can say time period decreases over here. And the second condition over here for frequency, that now becomes 1 by 2 pi under root G plus A by L. This implies frequency increases. So, one should understand, whenever the lift is accelerating vertically upward with uniform value A, then time period decreases and frequency increases. That is one area we have to concentrate on. Come to the third one. If the lift accelerates uniformly downwards, once again at A, we are considering the same acceleration, but the direction of its motion is opposite to that of the earlier case. It is accelerating downwards now. Then what happens to the relative value? Then relative acceleration that now becomes G minus A. And here one important theoretical point one has to remember is, one cannot write this equation as A minus G, because while moving downwards, any body cannot have acceleration greater than acceleration due to gravity. That condition, of course, every one of us should remember. Therefore, this now becomes G minus A, but cannot become A minus G. Then what happens to the time period? T will now be 2 pi under root L by G minus A. Since the denominator value is decreasing here, you can come to the conclusion that time period in this case increases. And in the same manner, what would be the frequency? It's 1 by 2 pi under root G minus A by L. This of course gives you that N in this case decreases. So, when it is accelerating upwards, these are the results, accelerating downwards, these are the results. Fine. There is one more case which I just write under this one, because D is the fourth case we are talking. If the lift either goes up or comes down with uniform speed, that is the concept. With uniform speed means one can directly understand that its acceleration will be 0. Whether the lift is at rest or the lift is moving up or coming down with uniform velocity or speed, in both the cases there will be no particular acceleration to that particular pendulum other than acceleration due to gravity. Therefore, the value of time period will be as it is, 2 pi under root L by G, and frequency 1 by 2 pi under root G by L. There will be no change as far as these two values are concerned. So, one should remember under two conditions, there will not be any change either in the time period or in its frequency. That is a point one has to remember. Now come down to the last case, please. That is the case E, the fifth one. If the lift falls freely, what do you mean by falling freely? Any freely falling body will have acceleration equals to acceleration due to gravity. That is what actually we all know. Therefore, one can write when it is falling freely, its acceleration is equal to acceleration due to gravity. And we all know well, when it is falling freely, relative acceleration becomes g minus a. And a and g, since they are equal, therefore what happens? This implies relative acceleration that now becomes 0. One should not term this one as acceleration 0. Understand this point carefully. Acceleration is not 0. Acceleration is equal to acceleration due to gravity. But relative acceleration is going to be 0. Therefore, the value of time period, which of course can be written considering this equation. So, time period now becomes infinity and frequency now becomes 0. What do you mean by frequency becoming 0? Frequency becoming 0 means the pendulum does not oscillate. So, that is ultimate conclusion one need to have. So, the pendulum does not oscillate in this particular case. That is one area you have to concentrate on. So, whenever that is in an elevator or a lift like this, then these are the different cases one should remember as far as time period and even frequency of the simple pendulum. But one thing more, frequency, the way in which it is varying in each and every case. Exactly like that, its angular frequency also changes. So, special mention need not be taken up as far as angular frequency of the pendulum that is concerned. Let us consider one more case like this, that is a simple pendulum is made oscillated from the roof of a car which is running on a flat road. So, let us once again take this one is the second case like, that is pendulum oscillating in a car. Moving on a flat road. Why we people are considering this flat road like? Concept is quite simple. The road even may be circular. Then the values are going to differ. So, let us consider the first case first. That is, on a flat surface, flat road, it is just moving with uniform speed it may move, or with uniform acceleration it may move, or with uniform retardation it may move. All these cases one has to remember. So, under that one, the first concept, if the car moves with uniform speed, then surely you can understand its acceleration is 0. Therefore, time period becomes 2 pi under root L by G and the frequency 1 by 2 pi under root G by L. So, absolutely no change as far as time period of the simple pendulum oscillating inside the car that is concerned. Similar is the case with the frequency. Now, come to the second one. If the car accelerates uniformly, at A, then what happens? One should understand a simple concept here. This is the pendulum on which the acceleration due to gravity is acting downward vertically, and the acceleration of the car is now horizontal like that. The angle between these two is since 90 degrees. Therefore, one can say the resultant acceleration that now becomes root over g square plus a square. The moment resultant acceleration becomes this much, then what would be the time period of the simple pendulum? 2 pi under root L by root over g square plus a square. So, surely the value is going to be greater than g. Therefore, what should be your observation? T decreases. Similarly, what is the frequency? 1 by 2 pi under root over g square plus a square by L. Then automatically one can say that frequency increases in this case. But one thing one should understand, it is accelerating I have given. There is a possibility for this particular car to retard uniformly also. That means, if I write this way, if the car retards uniformly at A, then also the resultant acceleration of that particular bob becomes root over g square plus minus a whole square. How much will this value be? Same as before, root under g square plus a square. So, what one should understand, whether it accelerates or retards, in both the cases resultant will be the same. Therefore, the time period once again will be 2 pi under root L by root over g square plus a square, which we can say that time period decreases. Coming to frequency part of it, 1 by 2 pi under root over g square plus a square by L, that implies frequency increases. So, there will be no difference whatsoever in the case of time period and frequency of the oscillating pendulum in the car, when either it is accelerating uniformly or it is retarding uniformly. That means, you can remember here it may be plus or minus a. Plus a means acceleration. Minus a, of course, you can represent that one as retardation. Whatever be the case, since the angle is 90 degrees between them, resultant will be this much only. So, accordingly, time period and frequency, they both are going to be similar by all respects. That is one more case one has to remember. So, this is the second case as far as the simple pendulum that is concerned.